Okay, folks, let's get started. First of all, good afternoon, and this is a non-paper session. And the topic is AI causing credibility crisis in networking? And my name is Ronaldo Ferreira. I'm a professor of computer science at UFMS in Brazil. And first of all, I would like to thank John and Walter, who will be joining here after I give a brief presentation, so we can hear from them too. And the idea here is to bring up this issue that is in the mind of a lot of researchers. So let's get started with a broader view in which machine learning methods are being widely adopted for scientific research for several reasons, right? It can achieve high predictive accuracy, it can handle diverse data type, you name it. I'm not gonna go through the whole list, and we can certainly put several other points that people find enticing to use. However, this widespread use of machine learning has come also with this concern about the models that we are using. Are they valid? Are they reproducible? Can they generalize? So these are the questions that are in the minds of several researchers in several different areas. For example, there have been several papers in different areas ranging from psychology, has looked at the problems with machine learning papers published, medical imaging, and the sciences in general, right? Just to list three. And this is actually, there are a much longer list of papers that we would find published about papers that were published that had some issue with some machine learning models. We ourselves published a paper about the use of AI, the machine learning in networking and security. So this widespread hype and optimism of the commercial AI is actually permeating and maybe affecting scientific research. These are questions that are things that I'm putting here that we should think about. Does it make sense, right? The problem is that if this is true, if they are left unchecked, these flaws can actually lead to a feedback loop of over-optimism. And what is the problem with that? Because we are building science on top of flawed science, right? And some papers show that sometimes non-replicable publications are cited more than replicable ones. And there are some studies that have shown also that AI, surprisingly, is actually slowing down the pace of scientific discovery instead of speeding up. So this is one of the papers that talk about these issues. So the question here is it different in networking? Are we doing anything different than the other fields are doing? Can we actually trust the models that we are using in our papers for solving network problems? Can they generalize? Can we reproduce? Are they credible, right? So the goal of this session, right, is to deal with three types of the audience, right? For those who are enthusiastic, the session aims to provide a more grounded perspective. For those who are skeptical, this session is meant to provide with some evidence. And for those who are neutral, and maybe a lot of us are, these are the three things that we thought, but there might be some other options. And this third point is maybe the most important. We should think about a roadmap for ensuring that networking in this age remains a science. And as John said yesterday, a science is about knowledge. Are we advancing knowledge? So using machine learning for solving networking problems is not new. So we have been using for more than a decade. But the past few years have seen a noticeable increase. And mainly because of more recent developments like GPT, LLM, foundation models. We have this great deal of excitement. You should, right? Like, they are doing amazing things, and we should not just discard. And also, when we think about networking itself, machine learning is viewed as critical for realizing these visions, such as self-driving networks. So we just cannot ignore. We just have to make sure that we are doing the right thing. So what is the impact of this? We can see this as two sides of the same coin. Thousands of publications in the networking area alone that are using machine learning, but there is little to no evidence that any of this work is used in practice. I mean, production networks. You always talk to network operators. Do you use machine learning in your backbone? Generally, the answer is no, right? One of the reasons that we notice, by the way, this is some work that we published in an editorial note in CCR this year. And one of the things that we notice is that the AI machine learning community have these modern machine learning pipelines that look like these shiny new objects, which is step-by-step instructions for training a particular model, which is basically readily accepted. And you have a lot of success stories. But the point here is that these pipelines are typically used without understanding its limitations, right? For example, we can say about the standard machine learning pipeline for supervised learning, RL pipeline for reinforcement learning, FM for foundation models, and you name it, right? What is this main component of the pipeline? Everybody knows about this. I'm going to go very quickly here. You have like a training task, you have a model specification, a training data set, sometimes labeled, and you have an evaluation process, generally with an IID data set, a copy of the training data. It generally goes like this. You collect some data, you select a model, you train, you test, and you evaluate, and depending on some performance measurements, like an F1 score, you might be happy, you accept, otherwise you collect more data, you select a different model until you get a nice F1 score. What are the key observations here? The sole focus here is on demonstrating effect, right? Which trained model performs best? There is no attention to understanding cause. How does the black box model work? So with this hammer in the hand, every networking problem started to look like a nail. And we can see that how machine learning has been used in so many different problems. So the question here is, what can possibly go wrong? There is this nice paper that was published recently from several researchers from Google. This is a paper that has 40 authors, that they showed that under-specification presents actually a challenge for credibility in modern machine learning. What does that mean? Is that most modern machine learning pipelines, those things that the ML community generally hand to us, are fundamentally flawed in the sense of being under-specified. It means that the pipeline that you use to train, they cannot specify the trained model in enough detail to capture essential structure beyond that training domain. And there exist so many different trained models with similar performance. So you can get different models that pick up different minima, that work well in some training data, but may not. Some of them might perform well in deployment, but most of them might not. So selecting the one model with the best performance means like F1 score, for example, defines a very low bar for declaring a success. There is also this problem of generalizability. Underspecified machine learning pipelines generally result in models that are not generalizable, means that are not credible. So they don't perform as expected in the target domain. They are unfit for real deployment. Generally, that's why we may not see a lot of real-world deployment of the thousands and thousands of papers that we see published almost every year. There are also a third problem that we mentioned here, which we call the giggle problem, the garbage in, garbage out problem, which the model's failure to generalize is generally underscores how critical the training data is, right? And generally appears in two forms, which we call shortcut learning, which is basically the models cheat on some specific features, or overfitting, that it becomes very particular to that data set and doesn't generalize. So, of course, cannot just say, oh, what are all these problems? So what can be done? One thing that we asked some time ago when we started looking at these problems, for example, some simple things. Ask probing questions. So what machine learning pipeline was used to training the model? What is known about the training data? How was it generated, collected, represented? And most importantly, how does the trained model make its decision? So how can you examine the decision-making of a black box model? So does the trained model engage in disingenuous learning? How can we check if the machine learning pipeline suffers from underspecification, right? And most importantly, when does the trained model work, not work, and why? How can we ensure that the model generalizes? So we published this paper at ACM CCS 2022, and it shows underspecification in networking security problem in some papers, a dozen papers that we look at. And here's the interesting thing about this issue. We were able to write this paper because all the papers that we analyzed were reproducible. The authors made available source code, data, all the artifacts. Because sometimes people think, oh, we had this problem with reproducibility in the past, you just release the code, the problem is solved, right? But here we have another dimension, because we were able to reproduce, we got the same scores, but when we started probing the models, they were not doing anything meaningful to that particular problem domain. They were just picking up some specific details with the data. Okay? So this is something that we should also think, because we always think, oh, we should have the artifacts available. Of course, it is important, but here we have another dimension, right? So typical reactions that we get when we talk about this work is that the enthusiasts would just say, well, but this is just another example. This is just one example. I say, fine, pick another example and investigate. You might be surprised. The pessimist says, I knew it. We say, well, keep doubting. And the neutrals say, so the problem is the machine learning pipeline. I say, no, well, it might be the training data, most likely, but also poor evaluation, lack of uncertainty quantifications can all be part of this problem. Okay? So this general obsession of demonstrating effect has come at a cost of ignoring or being indifferent to understanding cause. But this is a problem, right? If you do networking without science, automating production networks becomes a lot harder because operators cannot understand and trust. So given the flaws in these modern machine learning pipelines, their use for building credible models is compromised. So we need to think about going from demonstrating effect to understanding cause, so we can ensure that this research is sound. Okay? So if we prioritize understanding without demonstrating effect, this does not become credible models. And credible trained models are essential for us, especially for autonomous networking. If we think about our vision here, is that if we think about science asking those probing questions, maybe we can stop this huge amount of papers that are published and submitted every year. Maybe we can stop this crisis in reproducibility and credibility that we have been talking for the past 2 days. We got this in the keynote talk, also in the panels yesterday. And maybe, however, like the deployment might actually accelerate. So we need like stricter evaluation, new and better understood pipelines. Without answering these questions, how does the model work? Why does the model work? When does the model work? It's hard to believe in solutions, right? For example, one simple thing that we proposed in that same CCS paper, instead of having a simple pipeline that seemed to work in for other fields, or maybe not, why not having an extended pipeline in which after the evaluation you try to explain? This is one possibility. It's not the only one, and it's not the end of the story. Because here, in this case, we used one tool that we developed called Trustee that generates decision trees to explain black box model decisions, okay? And this extended pipeline was enough to find several problems in those papers. But also, besides the things that we did in the past few years, I would like to bring attention to a very important initiative that has started at Princeton with Arvind Narayana and his PhD student, Sayesh Kapoor. They had this workshop that they got together with several researchers from different areas to discuss the credibility of machine learning models, and they came up with what they called reforms, which is a consensus-based recommendation for machine learning-based science. See, the thing here is a lot of other areas are facing the same problems. They are trying to do something to prevent those problems. The question is, what are we doing, right? And the reforms initiative is like, we need to fix errors in machine learning-based science systematically, not just catch them after a paper is published. Otherwise, we have this cycle. Someone published a paper using machine learning model, and then a few years later, there is another paper pointing problems with that model, right? If we have clear rules, this will help researchers and also reviewers. And this is actually particularly important for young researchers when they're starting looking into a problem and they want to use machine learning. What should they do so the results credible? So despite this broad adoption, machine learning still lacks this common best practice, okay? And this ended up in a checklist for machine learning-based science. It consists of 32 questions with a set of guidelines. I do recommend you guys to take a look at this site, reforms.cs.princeton.edu. Those guys that are from Princeton will understand why we have different colors up there. And some journals in some areas are already demanding that when you submit a paper, you submit also a form saying that at least you did some basic evaluation. For example, in what situations you know that your model will not work? Did you quantify uncertainty? So all those questions that we should be probing are listed in this checklist. Also, Arvind and Sayesh wrote this very nice book called AI Snake Oil. I do recommend you guys to take a look at it. It shows a lot of interesting stories of models that don't work that well in practice. Things like you have an image from a lung that detects pneumonia, but in fact it picks up on the logo of the hospital, this kind of things, okay? So some parting thoughts until we get to our discussion. Edward Teller, a famous physicist, said once that the science of today is the technology of tomorrow, right? So in this case, if networking ceases to be a science, this critical infrastructure that we rely on the society use will be built in technologies that we don't understand, okay? So only by raising the bar, we can keep up with this pace and make sure that we provide foundations for future networking technology. The slides will be online, so I put some references here of some works that we published about this things that we had looked at in the past. I would also like to acknowledge my collaborators before we start our discussion. So I would invite John and Walter. Please come up.
Where do we go?
Please sit down. So first of all, I would like to ask both of you to give a quick view of you guys related to, are we in a crisis of credibility?
Okay, so, yeah.
Let me get the phone.
So I thought this was going to be about something slightly different, which is, do we have a credibility problem for people working on networking for AI? And I think we don't. I think a year ago I would have said we do, but when I look at some of the papers here, we have some really amazing engineering work with people optimizing networks and the pipelines for LLMs. Whatever you think about LLMs, the networking work and the systems work going on is extremely credible when you look at it. It's not necessarily very exciting, and I did want to point at a very cool paper 10 years ago by Frank McSherry and Derek Murray and Michael Izard, which was scalability, but at what cost? And they looked at all the papers back then on map-reduced systems like Hadoop, and they discovered there were tons of papers that said, oh, we get a 1.6x speed up. And when I look at LLM systems and network papers, it always seems to be 1.6x, which always makes me worry about maybe the paper was generated by an LLM. Why 1.6 times performance improvement is so common? But since these things have been around for 9 years, 1.6 to the power of 9 doesn't appear to have actually shown up as a performance improvement of these systems. So perhaps if you go back and look at the McSherry paper, he shows how all the different speedups are they're not orthogonal, so they don't all combine in any sensible way, but B, they never baseline them against the system, and actually many of the speedups cost you more to add the speedup technology than the speedup achieves. So I recommend people look at that paper. Another crisis area, which I think all of people in networking are aware of, is a beautiful paper called The Incredibles, which was about a crisis in network simulation, where I think at least 100 papers were shown to fail to do things simple like initializing and choosing random numbers and running the simulator to find the point where it went stable and blah, blah, blah. Many errors in this paper. And Incredibles, it's a beautiful read. But there's another thing which is the credibility problem of people working in networking systems for AI, which is the scale of the work, which is we really should be at the point when people do try and write the paper that combines all the techniques to see if they do multiply or add or do something nice. And the work to do that would probably take 1,000 people or 3 years or more, and they would have to have access to all the different hyperscale company platforms for doing this. So anyway, that was what I thought we were going to talk about. What I'm going to say to do with this is that there is hope, but it comes not from people working in the LLM world, but in science, in AI. We do a lot of work which has been around for a while now called PhiML. Hands up if you know what PhiML is, from the Greek letter phi, but it stands for Physics-Inspired ML. And what Physics ML does is it takes a first principles model, so the word model shows up, and you then train a machine learning system on data, but the architecture of the machine learning system, let's say a neural net of some kind, is derived from the physics model by mapping, let's say, partial differential equations into neural processes. So the architecture of your neural net is actually explainable by the physics model, but the actual system is trained on real data. So a concrete example of this, we did a project with Rolls-Royce on jet engine design. We take a jet engine, new jet engine. Rolls-Royce make quite good jet engines. You've probably all come here on planes with jet engines made by Rolls-Royce. So they put them in a wind tunnel, and they measure everything about them. And there's this kind of physics, there's fluid dynamics, and you've got these incredibly complicated differential equations. The same for weather prediction, by the way, but with the jet engine, it's easier to see. The partial differential equations describe what's happening. They tell you where there's laminar flow and turbulent flow and all these things, but you actually can't solve the things for any real scale system because the computational cost of computing the physics model is too high at the level of detail if you keep the level of detail the same everywhere to do the turbulence system. So you don't. You use the trained model that's derived from the physics model to figure out where things happen in the real world, and then you use that to train the solver for the PDE. It's not a SAT solver, it's just a finite element piece of computation. And you change the size of the finite elements, so you do really coarse grain where there's no variation much, and you do fine grain. So now you have a system which is efficient and completely explainable. And we did the same thing recently for some people in the British government with language models. So we go back to LLM. So we did a thing called lean language models. But we take a large language model and we add semantic data from old-fashioned NLP. So we have a model of the language, which is not a neural net trained model. It's actually a directly structured model from the principles of the language. And we use that to effectively prune and explain the LLM, and actually we use low-rank estimators to remove large parts of the LLM, so you get efficiency as well. So I think if you think of this world, could you do this to address this question? Could you take models of networks where you look at topology and the computational routing algorithms do in distributed route computation, or you take congestion control and maybe queuing models or other kinds of theories, and you combine them with machine learning, you do these hybrid models, because then you have the explainability, which is, I think, the really missing. And once you have explainability, you're going to get reproducibility, because you say, why is this model doing this? So that's my hope, that we could get some really smart people who have some good network theories, which have been around a long time, and then get them together with some people who are doing machine learning for traffic engineering, whatever it is, and then hybridize these.
Okay. So I'm probably taking a different approach to what John said, but aligned with what he says, but it's very different. So, are we in a crisis? So, what I would like to see now in today's world is we take this year's SICOMM submissions, sort them out, which one use AI or have checked the topic of AI, and look at these papers either on the submission side or on the paper accepted side. So I think if we look at the paper submission side, we end up probably with a couple of, of the, 300 submissions, probably half of them are AI, of the number of accepted papers. I think, I haven't checked that, but probably 20 or 30 of the papers have some sort of AI in there. And I think as a community, we should now go and do this as sort of an exercise. Take each one of these papers and go back to this sort of sets of questions that Ronaldo put up there, and sort of said, okay, for each one of these papers that uses AI, and make some claim about what that use implied. Do we know how that result was obtained, meaning which pipeline was used, what sort of model was used, and how does it work? Do we know when it doesn't work, and all that stuff? So basically go through this exercise of looking at these papers that we now have in our repertoire and come up with a list of questions that for the use of AI in networking would suggest that in the future, a paper that is being submitted to, let's say, SICOMM or some other conference in our area, an author who submits it has to fill out this checklist to along with the submission that sort of says, this work includes the following things that have been done, and yes or no, and be honest, of course. How do you check whether they're honest? But that would start to give us some idea of what, as a community, we should focus on in order to make sure that we don't just get any sort of yet another AI paper, but that each one of these AI papers have some scientific contribution that is worthwhile from a networking perspective. And I think without doing any of this sort of exercising to come up with a list that comes with a submission that each author has to fill out, it will be very hard for us sort of to prevent this crisis from continuing and getting worse. So I would like to see very much a concrete couple of steps that we as a community start to employ in order to make sure that the quality of papers that we see that use AI one way or the other increases as we move on from the current state, which I don't think looks very good. So.
All right, thanks, Walter and John. Please, the audience, someone would like to make a comment, ask questions, please raise your hand. Here.
Hi, Sagar from UC Irvine. And by the way, I think a lot of great ideas were proposed here, and I also see the hope in making efforts to build proper science into AI for networking. And I think a lot of the steps you guys are proposing, will go a long way to making this roadmap a reality. I think the one comment I wanted to add was also to have humility around the form and the evaluation criteria itself. So, I'm an explainability person, by the way. I published an explainability paper due to SICOMM' yesterday, but I will be the first person to tell you that explainability isn't a good science in general, because the main argument for against explainability is the fact that if there is data under specification problem in the original problem, there's also data under specification explainability problem. So you will produce an explanation that is also underspecified and can change if you just rerun the same code over and over and over and again. And so the point I'm trying to make is that if, for example, we are very headstrong about incorporating explainability into one of the evaluation criteria, we should also acknowledge that, or maybe that might not be a great idea, and perhaps have a way to change how we evaluate models themselves, rather than adopting, F1 scores were a bad idea, okay, let's go to this quantization score, and stick to that and produce all of those types of things.
Yeah, I think you are absolutely right. There are also papers that complain about the use of explainability, but from our experience at least, explainability was useful to show basic problems that the authors didn't even consider. And we could make sure that there was a problem, because we look, okay, this doesn't look right, because just to give you a sense, we had a paper that we analyzed. It had a convolutional neural network with 6 million parameters, and we generated decision trees to see if we could get anything out of it. And we got really surprised when we ran several times and we got decision trees with 7 nodes. Always. 7 nodes was explaining the whole decision process. And that helped us to see where the problem was. With the data was not even treated properly. We're not claiming that explainability is the way, but we have to ask those questions and see what are the best way of answering those questions. Okay, Walter. Oh, John.
So another technique from the AI world, which I'm a big fan of, along with PhiML, is causal inferencing. And there's at least one paper this year in SICOMM mentioned it. There probably are more than one. And the really cool thing is it quite often uncovers latents that you didn't know about, so you can actually then fix your model. And so I think, there are AI techniques which are incredibly valuable. I've seen a few years ago, there was a China mobile paper on causal inferencing and fault diagnosis in their network. It was extremely good. They had a couple of real world examples, and if you read Judea Pearl's book, The Book of Why, which is sort of the main textbook in this area. They basically took that and did a use case, or, but it's that's really neat because it goes beyond saying, you want explainability of model, you're going to use an approach that gives you an explanation, which is really cool. And you can do that with PhiML as well. So there have been people who had non-complete first principles models from physics, and they've uncovered missing pieces of, missing parameters in their system by using effectively something like causal inferencing, and then improve the structure of the model so that they'd overused Occam's razor in the first place. So I don't think, I agree. Explainability and transparency or interpretability are not a panacea, but I think they are very useful. And then I think, like I say, if you have these alongside some principal model, which may not be complete, it may not explain everything, but the combination can improve qualitatively and quantitatively. So I think this is like why there's and there are people here. I've seen people doing work in the networking community where they do AI for traffic engineering. There've been a couple of papers. I think NSTI's have one from Michael Shapiro and other people, which had all those sorts of properties, and I think there are other papers like that. So there are people out there getting it, and we should sort of celebrate those so that we create a kind of beacon of what's what is good practice. And then we've heard this introduction where there's sort of actually principles for good practice too. But yeah, it isn't just one thing. There are many components to it. So good question.
Yeah, I mean, I completely agree in terms of being humble here is absolutely necessary. Any attempt to try to sort of steer or come up with sort of forms that sort of tell authors the expectation that a conference has for a paper in this area, we will get wrong at the first stage. It needs to be constantly updated, modified, adjusted, because this is an experiment that we would have to do, and getting that right in the first place is certainly not what we expect. But doing it, getting it started, I think, is the important thing, so that authors that submit to Conference X have an expectation of what is expected from the paper, and if the paper doesn't satisfy those expectations, they shouldn't be surprised that it doesn't get in. That should be clear, and right now it's not clear.
Yeah, and we can always think about things that we have been doing the past few years to improve our research. One thing that came up like in the last 5 years, we never talked about ethical concerns, right? And now most of our conferences, you have to write some section about ethical concerns. So maybe we should think about, okay, here are a paper that uses AI. What should we expect to see from the authors? What did they do to make sure that they are not just, going for the low bar? Any other comment, please? Sure.
Hi, Dave Moran. I'd like to poke at a different thing. We have a whole generation of trying to understand what data to collect from a network in order to allow a human operator to figure out what's going on, when there are problems, what the root cause is, and how to configure a network based on what we've collected. And now we're taking that same data, feeding it into a magic black box, and the expectation is that it's going to do a whole lot better than the people do. And I'm not sure we have evidence for that yet, but even if we do, what we've discovered from other problem domains, radiology is probably the poster child example, is the thing a good AI model needs in the training data and actually to outperform a human being is actually fairly different from what the human being uses in terms of the collective data to make their decisions. So my question would be, is there something wrong with the data we are collecting from networks that is going to limit how much better an AI-generated model can do for analyzing problems, finding root causes, and configuring networks than what we have today? Should we start looking at collecting different data that would be friendlier to the way an AI model uses the training data to actually make predictions? Thanks.
You want to take it? Walter did a lot of work on this front with data.
So, I mean, again, so my starting point has always been, so we look at a particular problem that in networking that we want to solve with AI. And the tradition has been you pick a model specification, and then the training data is an afterthought. You pick a training data set that is publicly available because you don't have one yourself, and you don't know who generated it, in what way, and all that stuff. And that has been sort of pretty much a standard approach in the past. And the question really is, if we would be more honest about answering this question, what is the right data set for my particular problem? The answer in general will be, I don't know. Now, we can move away from that sort of baseline by going your direction, and sort of there are domain experts that can help us decide what is the right data set for this particular problem. They may not have all the knowledge either. So there is sort of a belief that if you have now the capability of pretty much measuring everything in your network, you could throw the kitchen sink at your problem, and the model picks out relationships that even the experts sort of haven't even thought up front. But once they see that this can be extracted from the data, they say, oh, I didn't think about this, but it makes sense. I mean, so that sort of loop of, using AI to sort of even interact with a domain expert to sort of say, does this make sense that comes out of the data? Yes or no? If the domain expert says yes, then it's an indication that maybe we have a way to move forward. If he says no, or she says no, then we know that the model hasn't been doing sort of what it's supposed to be, and potentially makes mistakes that we would like to avoid. But I think there is a process to move in a direction where we actually get to the stage where it says, for this problem, this is the right training data. But we are not there.
So what do you collect, what information do you collect, and how far do you go for it? So I have 3 little stories from when I worked at UCL in early internet days. Every Friday we have a room full of machines that crashed somewhere between 3 and 4 p.m. And there are 2 stories in one, but it turned out that I was like trying to work out, why do all these machines shut down and, at this point? And then somebody pointed that there was a really large electrically powered crane on the site, and they only did the loading and unloading at that time on a Friday, and they pulled enough current that the voltage dropped below what the system could stand. The second reason, and the same thing, but a completely different reason, was most people logged in on the, let's say it was a PDP 1144, running version 6 Unix, to do their coursework on a Friday, and the AHU packets exceeded the buffer size in the PCs we were using and overran the end of the buffer, and they all crashed. And so how would you discover these things from an AI? And the third one was I was doing a measurement of SATNet for SICOMM'25 paper. The SATNet was a geostationary satellite across the Atlantic, went between Europe and North America. And I was getting really, really bad throughput compared with normal. And my office mate was an astronomer, and he pointed out the window, and there was a massive lightning storm. And basically there was just interference happening at a way higher rate than normal. So, these are 3 things where when you talk to network operators, they tell you stories like that. And I have literally no understanding of how any AI is built to get that kind of qualitatively broad, weird external input knowledge, but actually that's why you keep really smart people operating networks, because they kind of go, oh, wait a second, it could be this really weird thing over here. Whereas if you're using AI to do something that's just an improvement over a traffic engineering algorithm, like the paper I mentioned by Shapiro, I'm trying to remember, he did 2 papers and they're both pretty neat. The understanding of what the system should do compared with a classical approach, with just some standard ILP-based optimizer, whatever it happens to be, was very clear. So it was very easy to see that. But when you're doing these fault-type problems, then it's a way different problem because it's a weird, well, basically, in AI terms, you're doing search over a very strange landscape. It's got a structure that's really odd. So it's got, you know, no nice kind of smooth behaviors anywhere. But that's actually probably where the interesting problems are as well. Yeah, I was going to go back to the first principles model because a lot of this comes out of Bell Labs, and you know, when you first do radio and you want to work out what the coding modulation you should use, and you've got something that's trying to figure out what does this signal mean in terms of bits, and you build a maximum likelihood estimator, and the MLE is based on the actual statistics. You went out and got a meter and measured the radio on a spectrum analyzer and measured what was happening with the real interference distribution. Not with lightning storms. And then you could build what's the likelihood estimator look like because you know the distribution. So you have this model here, which tells you how to do this estimate of what you're actually getting. Where are you in that population of possible results? So that's like, how old is that? 100 years old? 75 years old? I don't know. When did it happen between Marconi and Bell Labs? But it's a very, very old thing, that approach, which I think is very sound.
All right, I think unfortunately we have run out of time. It went much faster than I anticipated. So I'll be glad to talk to anybody about this issue, and I hope we have brought some, new perspective to the problem and that the community thinks more carefully about these things, okay? Thanks, John, thanks, Walter, and thanks everybody for coming.